All right, so this video is to show how we can derive the statement about an adiabatic gas undergoing compression or expansion that PV to the gamma is constant. First, what do we mean by adiabatic? We mean that there's no heat transferred in or out of the system. So if our change in internal energy is change in heat plus work done on the system, our delta Q is 0, so the internal energy is just work done on the gas, okay? And I'm going to show you two different ways to derive this, one of which is shown in your book, and then a second one just to show you sort of two different ways to manipulate these state variables, okay? So we'll start with writing this statement about the change in internal energy. And we're going to talk about an infinitesimally small change in internal energy. So instead of writing delta E, we'll write d E internal. And remember, we can write this in terms of CV, the heat capacity, constant volume, times dt, right? That's just what our heat capacity means. And then this equals negative P dV, because that's our definition of dW, okay? And then this equation, as we have it now, is not easy to integrate, right? Because pressure here depends on both temperature and volume. So we need to fix that so that we can get an equation that we can actually integrate. All right, so to do that, we're going to write our ideal gas equation, PV equals nRT. We're going to solve for P, substitute it into our equation here. So then we will have that CV dt equals negative nRT over V dV. Now, temperature on the right is a variable, right? And so we need to isolate our variables. And so we're going to move that temperature over to the left side of our equation, giving us an equation that looks like this. And now all of our variables are separated. The CV and the N and the R are constant here, okay? And so now we have something that we can actually integrate, okay? And again, just to do this the same way as your book, I'm going to divide both sides by CV. So my CV moved over to this side of an equation, right? And then when I integrate this, I will get that log T is negative nR over CV log V plus some constant of integration, all right? And now I can move this over to the other side of my equation. So I get log T is, right, plus nR over CV log V is a constant. And now I'd like to be able to manipulate this equation so that I can put these two logs together. So to do that, I'm going to notice that I can move this term into an exponent, all right, to where then I will have just two logs to add together. So I'm going to do that. And then now I can combine these two logs, right? So I get that log T V to the nR over CV is constant, right? And I'm going to use the result that we derived before, that CP minus CV is in R, okay? And so now that means that this term in my exponent here is CP minus CV over CV is CP over CV minus 1. And then this thing, CP over CV, is our definition of gamma, so that's gamma minus 1. So this tells us that log of TV to the gamma minus 1 is a constant. And of course, if that's a constant, then the part inside the logarithm must also be a constant. So TV to the gamma minus 1 is a constant. All right. And then the way we wrote this earlier was that PV to the gamma is constant. We just get that by remembering that PV equals nRT. So T is PV over nR. And that means that V times V to the gamma minus 1, which is just V gamma, is times P, is nR times a constant, which means that that's just also a constant. Again, it's a different constant, but we don't care what that constant is. So we just write PV to the gamma as constant. Okay. So that's one way of doing this proof. I want to show you another way. I think this way that's in your book is easier, but I want to show you another way just to give you